Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on zeros, singularities and poles, lecture number 12, in which I will solve some remaining problems of this chapter. Now we solve a problem. Problem is find the zeros and singularities of function of z fz equal to z minus 3 sine 1 by z plus 2. Since for z plus 2 equal to 0, the function fz is not defined, implies that fz is not analytic. Therefore, z plus 2 equal to 0 will give a singular point. Implies that z equal to minus 2 is a singular point. For zeros of fz equal to 0 implies that z minus 3 sine 1 by z plus 2 equal to 0 implies that z minus 3 equal to 0 or sine 1 by z plus 2 equal to 0. When z minus 3 equal to 0 implies that z equal to 3. Therefore, z equal to 3 is a 0 of function of z. This is number 1, this is number 2. When sine 1 by z plus 2 equal to 0 implies that 1 by z plus 2 equal to n pi, n equal to 0 plus minus 1 plus minus 2 dot dot dot. Implies that z plus 2 equal to 1 by n pi, implies that z equal to 1 by n pi minus 2. These are zeros of fz. Limit n tends to infinity, z equal to limit n tends to infinity 1 by n pi minus 2 equal to minus 2. Therefore, limit point of zeros equal to minus 2. Therefore, z equal to minus 2 is an isolated essential singular point. Therefore, number 1, z equal to 3 is a 0 of function of z. Number 2, z equal to minus 2 is an isolated essential singular point. Now we solve the next problem. Next problem is show that the function e to the power minus 1 by z square has no singular point. Let function of z equal to e to the power minus 1 by z square implies that function of z equal to 1 by e to the power 1 by z square. For singular point, denominator equal to 0 implies that e to the power 1 by z square equal to 0, which is not possible for any value of z which is either real or complex. So fz has no singular point. For 0 of the function fz equal to 0 implies that e to the power minus 1 by z square equal to 0 implies that e to the power minus 1 by z square equal to e to the power minus infinity implies that 1 by z square equal to infinity implies that z equal to 0. Therefore, z equal to 0 is a 0 of function of z equal to e to the power minus 1 by z square. Now we solve the next problem. Find the kinds of singularities of fz, function of z, equal to z minus 2 by z square sine 1 by z minus 1. Solution. Since for z equal to 0 and z minus 1 equal to 0, the function fz is not defined. Therefore, z equal to 0, here twice, z equal to 0 is a pole of order 2 and here z equal to 1 is a singular point. Now we verify the kind of this singular point. For 0 of fz, the numerator equal to 0 implies that z minus 2 multiply sine 1 by z minus 1 equal to 0 implies that z minus 2 equal to 0 or sine 1 by z minus 1 equal to 0. When z minus 2 equal to 0 implies that z equal to 2. Therefore, z equal to 2 is a 0 of function of z. Here this is number 1, this is number 2, this is number 3. When sin 1 by z minus 1 equal to 0 implies that 1 by z minus 1 equal to n pi, n equal to 0 plus minus 1 plus minus 2 comma dot 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 implies that z minus 1 equal to 1 by n pi, implies that z equal to 1 by n pi plus 1. These are sequence of zeros. Limit n tends to infinity, z equal to limit n tends to infinity 1 by n pi plus 1 equal to, if n equal to infinity, this is 0, remains only 1. Therefore, z equal to 1 be the limit point of zeros. We know that limit point of zeros be an isolated essential singular point. Therefore, z equal to 1 is an isolated essential singular point. Here in 2 we have declared that z equal to 1 is a singular point, and we have verified here that z equal to 1 is an isolated essential singular point. Now we solve the next problem. Problem is find the nature and location of singularities of the function fz, function of z equal to 1 by z under bracket e to the power z minus 1. Prove that function of z can be expanded in the form 1 by z square minus 1 by z plus a naught plus a2 z square plus a4 z to the power 4 dot 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 when modulus of z is greater than 0, less than 2 pi, and find the values of a naught and a2. Now we solve this. For singularity of the function, denominator equal to 0, this is denominator, this 0 means z equal to 0 or e to the power z minus 1 equal to 0. When e to the power z minus 1 equal to 0 implies that e to the power z equal to 1, implies that e to the power z equal to 1 means e to the power 2n pi I. Since e to the power 2n pi I means cos 2n pi plus I sin n pi, and value of this is 1. Here z equal to 2n pi I, n equal to 0 plus minus 1 plus minus 2 and so on. Here we see that z equal to 0 is a pole. Here also z equal to 0 when n equal to 0 is also pole. Therefore z equal to 0 is a pole of order 2, and z equal to plus minus 2 pi I plus minus 4 pi I are other poles. Putting values of n plus minus 1 plus minus 2, we get value of these. These are simple poles because 2 pi I appears once, minus 2 pi I appears 1. Similarly, z equal to 4 pi I appears 1, minus 4 pi I appears 1. So these are other simple poles. When modulus of z is greater than 0, less than 2 pi, then the function fz may be expanded in Lorentz series as follows. Here we have seen that z equal to 0 is a pole of order 2, and we have bounded that this between modulus of z lies between 0 and 2 pi. So we will not consider other simple poles here. And in this case, number of turns in principal part be 2. Z equal to 0 is a pole of order 2 only. Here, this is the singularity here. We know that if a z equal to 0 is a pole of order 2, then number of terms in principal part of the function will be 2. That will be b1 by z plus b2 by z square. Z means z minus 0. Here z square means z minus 0 whole square plus other terms. Now, function of z equal to 1 by z multiply under bracket e to the power z minus 1. We put the value of e to the power z here and minus 1. Here 1 and minus 1 cancel out. So we take common z. So here we have already z and we take common z and becomes z square. Here remains 1. 1 plus z by 2 plus z square. We have already taken common z. Here remains z square by 6. Similarly z cube by 24 and plus dot 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 and to the power minus 1. So we use the binomial theorem. 1 plus x to the power minus 1. This is 1 minus x plus x square minus x cube and so on. So here we take this as x. 1 minus this x plus x square minus x cube and so on. Now we rearrange all the terms. We get outside 1 by z square. Here 1 minus z by 2. Here under bracket minus 1 by 6 plus 1 by 4 z square plus under bracket minus 1 by 24 plus 1 by 6 minus 1 by 8 z cube. Here plus under bracket minus 1 by 120 plus 1 by 36 plus 1 by 24 minus 1 by 8 plus 1 by 16 z to the power 4 plus dot 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 dot. And this equal to 1 by z square under bracket 1 minus z by 2 plus 1 by 12 z square minus 1 by 720 z to the power 4 plus dot dot dot. We multiply each term of the bracket with 1 by z square. We get 1 by z square minus here remains z minus half here z plus here z square cancel plus 1 by 12 here z square here z to the power 4. So remains minus 1 by 720 z square plus dot dot dot. This term is a naught and this is a2. Coefficient of z square is a2. Therefore a naught equal to 1 by 12 and a2 equal to minus 1 by 720. So the expansion of function of z within modulus of z greater than 0 less than 2 pi be this 1 by z square minus 1 by 2z plus 1 by 12 minus 1 by 720 z square plus dot dot dot, and a naught equal to 1 by 12, a2 equal to minus 1 by 720. So our problem is solved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.